scientists just discovered the biggest structure in the universe. So big, it might challenge everything we think we know about cosmic structures. A new study published by a group of astronomers has just identified the largest known structure in the universe, which they named Quipu. It was part of an effort to understand how massive structures influence the cosmic web, galaxy formation, and even measurements of the Hubble constant. So what exactly is Quipu? It is a vast collection of galaxy clusters interconnected by huge filaments. The authors describe it as a long cosmic filament with small branching filaments. This is how they coined its name Quipu, which refers to the knotted cords used by the Inca civilization to record information. But the structure is huge, estimated at over 428 megaparsecs or 1.4 billion light-years long. It has an estimated mass of 2 × 10 to the power of 17 solar masses, and it's thought to contain 68 galaxy clusters holding billions of galaxies and a huge fraction of cosmic matter in this region. But how does this compare to other known large structures in the universe? On the smaller end of the scale we have the Shapley supercluster. At a mere 90 megaparsecs or 300 million light-years, it's significantly smaller but is considered a very dense structure. Next up is the Sloan Great Wall, still smaller at around 328 megaparsecs or 1.07 billion light-years in length. There is one structure that dwarfs all others, the Hercules Corona Borealis Great Wall, stretching an astonishing 3,000 megaparsecs, which is 10 billion light-years across. However, its existence is highly debated. The issue lies in how it was detected using gamma-ray bursts as tracers of large-scale structure. Unlike galaxies or clusters, gamma-ray bursts are rare, short-lived, and difficult to pinpoint precisely in redshift space, making it hard to confirm whether they truly outline a coherent structure. This uncertainty has kept the Hercules Corona Borealis Great Wall in a grey area of cosmic structure studies, an intriguing possibility, but not a confirmed reality. Unlike this, the discovery of Quipu rests on much firmer observational grounds, thanks to X-ray data. Researchers identified it using a friends-of-friend algorithm, which connects nearby galaxy clusters based on their separation to map large-scale structures. The key advantage is that instead of relying on indirect traces like gamma-ray bursts, Quipu was found using the classic survey, which tracks galaxy clusters by their X-ray emissions. This approach is far more reliable for mapping mass distribution because X-ray emissions directly trace hot gas within massive clusters, allowing astronomers to precisely determine their position and redshift. The team confirmed that Quipu stretches across a redshift range of 0.027 to 0.065, revealing a structure of immense scale. Even more intriguingly, Quipu may extend beyond the zone of avoidance, a region where our Milky Way's dust obscures observations, meaning this massive structure could be even larger than currently measured. So why does this matter? Structures this large aren't supposed to exist, at least not if the universe is homogeneous on large scales. So does Quipu break the Big Bang model? The cosmological principle states that the universe should be homogeneous and isotropic on large scales, meaning if you zoom out far enough, matter should be evenly distributed. According to lambda cold dark model cosmology, structures like galaxy clusters and filaments form from small density fluctuations in the early universe, which grows over time due to gravity. However, there's supposed to be a natural limit, around 300 megaparsecs, beyond which structures blend into a smooth distribution. Quipu is 428 megaparsecs long, well beyond this supposed limit, raising the question, are these ultra-large structures breaking our models? Interestingly, simulations, based on the standard lambda cold dark model, do show the formation of some superclusters like Quipu. The researchers found similar structures in the Millennium simulation, a computer model of the universe's evolution. But does this really mean that they naturally form in a lambda cold dark model universe? The key lies in how these structures are identified. In the simulations, the researchers used a friend-of-friends algorithm with a linking length of 38.5 megaparsecs to group nearby galaxy clusters into superclusters. This linking length is a threshold distance that decides which clusters are considered connected, but it's a parameter we choose, not an inherent property of the universe. By adjusting the linking length, you can make clusters appear more connected, merging into larger structures or breaking them apart. In other words, the size of Quipu depends partly on how we define and measure it. This reveals something fundamental about cosmology. It's all about the models used to interpret the data. By choosing a particular linking length, we're not just analysing the universe, we're imposing a framework that decides where connections begin and end. In doing so, we might be creating links that don't actually exist in reality. Instead of proving Lambda-Coldalk model can explain Quipu, these simulations show how assumptions in our models can shape our understanding of cosmic structures, blurring the line between discovery and interpretation. The missing integrated Sachs-Wolf effect. The integrated Sachs-Wolf effect occurs when cosmic structures distort the cosmic microwave background. Superstructures should leave a hotspot due to the way photons gain energy passing through evolving gravity wells. The Quipu researchers searched for this effect in the Planck satellite data and found nothing significant. If Quipu really is this massive, why doesn't it leave a strong imprint on the CMB? The absence of a strong integrated Sachs-Wolf signal suggests a deeper problem with how the Lambda-Coldalk model connects cosmic structure, dark matter and the CMB. The Lambda-Coldalk model assumes dark matter drives structure formation, creating the early density fluctuations that later grew into filaments, walls and voids. If Quipu exists on this scale, then the gravitational effects of this mass should be obvious, but the missing integrated Sachs-Wolf signal suggests that something is off in this picture. If the CMB truly represents the leftover radiation from the Big Bang, then large-scale structures should interact with this in predictable ways. The lack of integrated Sachs-Wolf imprint suggests that the CMB isn't actually a direct relic of the early universe, but something else entirely. This directly connects to alternative interpretations of the CMB, which I've covered in my previous video, so if you haven't seen that, I highly recommend checking it out. Quipu's missing imprint isn't just a small anomaly, it highlights a fundamental disconnect between the key elements of the Big Bang model. This strengthens the case that we might need a radically different framework for how we interpret the origins of cosmic structures, the true nature of the CMB, and the role of dark matter in the universe. If Quipu's sheer size already pushes the limits of cosmic structure formation, and its missing CMB imprint adds to the mystery, then maybe it's time to consider other explanations. Could we be looking at evidence for an alternative cosmic model? The plasma cosmology perspective. Plasma cosmology suggests that electromagnetic forces play a dominant role in shaping large-scale structures. If filaments in the cosmic web are actually Birkeland current, massive plasma structures carrying current across intergalactic space, then structures like Quipu could be a natural outcome. This would mean large-scale structures form more rapidly and can extend over greater distances than the Lambda-Coldalk model predicts. The CMB could be local microwave radiation rather than a relic of the Big Bang. And Quipu's missing integrated Sachs-Wolf effect makes sense, because the CMB may not be interacting with large-scale structures at all. Plasma cosmology still lacks detailed simulations on the same scale as the Lambda-Coldalk models. Modified gravity and large-scale flows. Some alternative models propose that gravity itself may behave differently on cosmic scales. MOND and emergent gravity models suggest that what we call dark matter might actually be a misinterpretation of how gravity works over vast distances. If Quipu's mass isn't behaving as expected, not pulling on the CMB as much as it should, could this be evidence that gravity does not work the same way at these scales? The challenge. These models still struggle to fully explain cosmic microwave background patterns. Inhomogeneous universe models. What if the universe isn't actually homogeneous at large scales, as the cosmological principle assumes? The Lemaitre-Tolman-Bondi model suggests that our local universe could have density variations that affect how we interpret cosmic expansion. This could mean cosmic structures like Quipu are not anomalies. They are evidence that the universe is clumpier than expected. If large-scale inhomogeneities exist, our measurements of the Hubble constant and dark energy may be skewed. The integrated Sachs-Wolf effect might be weaker in certain regions simply because CMB photons are passing through under-dense regions. The challenge. This model would require a major rethinking of cosmic expansion and standard candles like SN1A supernovae. Unknown factors, or something we haven't considered. The missing integrated Sachs-Wolf effect suggests a gap in our understanding of the interactions between large-scale structures and cosmic background radiation. Could Quipu be part of a new class of structures that form outside our current models? Is there an unknown interaction between matter and radiation that we don't yet fully grasp? Future surveys and deeper observations may provide new clues, or even force us to rethink our cosmic models. Quipu is interpreted as a filamentary structure in the cosmic web because all its clusters fall within a narrow redshift range, suggesting that they are at a similar cosmic distance. But they don't seem to be gravitationally bound, meaning they're not moving towards a common center, they're just correlated in redshift space. But what if that assumption is wrong? Astronomer Halton Arp proposed that redshift might be an intrinsic property of galaxies, occurring in quantized steps. This would lead to walls of galaxies at similar redshifts, but not because they are at the same distance. Instead, they would be spread out in space, but we would misinterpret them as being connected structures due to their quantized redshifts. If this is true, then Quipu might not be a connected structure at all. We'd just be misinterpreting it as one because we're seeing galaxies at similar redshift steps. This would challenge our entire model of cosmic structure formation. The discovery of Quipu raises big questions, not just about how large-scale structures form, but about the very foundations of cosmology itself. Quipu is the largest confirmed structure at 428 megaparsecs, bigger than the Sloan Great Wall and beyond the expected size limit of cosmic structures. It challenges the cosmological principle which assumes that the universe is smooth on large scales. Its missing CMB imprint suggests a disconnect in how the lambda cold arc model links dark matter structure formation and the CMB. Simulations show similar structures, but they rely on choosing a link length that groups clusters into large structures. Are we seeing real cosmic connections, or is the model creating them? This points to a deeper issue in cosmology. The assumptions in our models shape how we interpret data. If we adjust the parameters to find structures, are we discovering reality or imposing it? This echoes Halton Arp's warning that redshift interpretations could be creating illusionary structures, not because they're actually connected, but because of how we choose to interpret their redshifts. Quipu doesn't just challenge lambda cold arc model, it challenges our confidence in the frameworks we use to understand the universe. Open questions and future implications. Is Quipu a real physical structure or a product of our models? If the linking length used to find it defines its existence, then it raises the possibility that we're seeing patterns that aren't actually there. If more structures like Quipu are found, will it break the 300 megaparsec size limit or force us to reconsider how we define connected structures? Could this discovery be part of a large pattern of inconsistencies in the lambda cold arc model, similar to the Hubble tension and the CMB anomalies? Does the missing integrated Sachs-Wolf effect suggest that dark matter isn't behaving as expected, or does it challenge the nature of the CMB itself? And most importantly, are we building a model of the universe, or is the model building our understanding of the universe? Quipu isn't just another cosmic structure, it's a mirror held up to cosmology itself. If our models are leading us to see patterns and connections that might not be real, then how much of our understanding of the universe is truly objective? This resonates with Arp's critique of redshift quantization. Are we misinterpreting redshift patterns as physical structures because of our underlying assumptions? Quipu may just be one structure, but its implications ripple through multiple areas of cosmology. Are we missing something fundamental? Do we need new models, or is it just another piece of the puzzle we haven't fully understood yet? I'd love to hear your thoughts. Does this discovery challenge the Big Bang model, or is there another explanation? Let me know in the comments. And if you want to explore the deeper problems of the CMB and cosmic expansion, check out my previous videos where I break it all down.